structures, and also some other related topic. Before going for those research and some of the industrial work that I have done, want to just give some introduction about myself. I got my PhD in Iran in 2019, and then I was working as postdoctoral researcher with Southwest University of China for around 2 years. From 2022, I moved to Ireland, and I was working as postdoctoral researcher at University College Dublin for around 3 years. And from 2025, I moved back to industry, and I'm currently working as research engineer in Ronald O'Donovan, a consultant company in Ireland. During my career as a researcher, educator, and industry engineers, the main focus of my project and research study was in related to application of and developing of different AI models for infrastructure assessment. And mainly it can be divided to 4 categories. Over almost 12 years of experience, I was working on different branch of structural health monitoring, such as drive-by and indirect health monitoring of infrastructures, and also direct assessment of transport infrastructures using installing sensor and some other device. I also was working on wind energy infrastructures for developing a method and models for health monitoring of different wind turbine, both offshore and onshore wind turbine. And also we extended our work to different buildings and also industrial assets such as train wheels. And mainly I'm currently working on using data-driven methods and AI for intelligent transportation systems and traffic management, and how we can somehow bridge the gap between what data and information that we have in a specific field and the knowledge of the data science and data mining, and correlate these two branch of science to have better insight about the current or future state of our infrastructures. When we are explaining AI, it will be better to, first of all, have some a general understanding of different steps that we usually have for using different data mining and AI model for infrastructure assessment. Generally, we can divide the process to 3 main steps. First of all, we need some data to be able to process and do some work on those data. Next steps, we need to create some models or select some model for preparation and somehow link the data and do some manipulations and some process on that data, and find at the end, when we have our model and when we have our data, we can extract some information from the raw data. In this case, and in structural health monitoring or ITS application, we usually have some data that comes from different sensors that have been installed on bridge or wind turbine, or it can be a sensor that have been installed on road for detecting number of vehicles. We have data, or in some cases, data can come from finite element model or digital twin of the infrastructures or road. When we have the data and we process the data and select our model, we can go and have some insight about the current state of the structures, is healthy, is damaged, or about the current condition of the more sophisticated systems such as traffic, to know, for example, what is the current condition of the road. Is there any congestion on the road? Is there any incident there? And the idea is to combine the techniques together to have better insight about the structures. These 3 steps can be more explored and can be divided to more sections when we want to go for pipeline development, when we want to go with a step-by-step approach for our data and processing our data, and also for interpreting the data. One of the main research question that I tried to answer during my research study, both in my PhD and postdoc and currently in my industrial work, was to know from different components of the system which component have the highest impact on the output that we can have. Is input data that we can insert to the model, or the output that we can expect from the systems and the model that we can use from the different catalog of models that we can use. We can go with shallow ML models such as support vector machine, artificial neural network, or with more sophisticated deep learning model, or with the current AI tools such as large language model. So my question mainly focused on link between two, and my research was mainly on link between these two, which is feature engineering, is the link between raw data and the model, which somehow remove some of the data, some of the noisy data, and select those part of data that is important for our model to be developed. Feature engineering also have different steps and different terms that I don't want to go into detail in these sessions, but my research focus was to somehow find a set of easy extractable feature from different structures and infrastructures that can be used for health monitoring and also for traffic monitoring conditions. I will go with some of the research work that I collaborated or I lead them during my time in UCD, and also some of the work that I am currently doing in R&D. And it's divided to different categories that I've shown in the slide 3. As I will start with transportation infrastructures, and specifically for a project that we had for railway track monitoring. As our goal was to assess and see how we can use data for knowing the condition of railway tracks. We used two different data sets, and we was collaborating with two different organizations. First, one of them was a railway track company in Pittsburgh, when they recorded a series of data from a set of sensors that was installed on train, and it was traveled around a 43 kilometer of road near to Pittsburgh, and it was record acceleration response data that was recorded on train, and the sensor position can be seen on train. And the other data set that I was working on that was related to another project with railway company in France, where they installed different sensor on train, and this train was moving around a high-speed network of France and was recording acceleration response data and some other data. And the main goal was to use those data, which was massive set of data, for detecting the condition of the track in, for example, geographical and different geometrical defect that we can have in track. As I mentioned, the first data set was DR10 data set, and the data set that was from Pittsburgh. And in that data set, we have data from 3 types of sensors. Some of them was triaxial accelerometer, some of them was uniaxial sensor, and some of them was data from the maintenance activity that have been implemented on that section of the road. The goal was to somehow correlate the data that we have from acceleration sensors to maintenance activity that is needed for that section of the road. Different maintenance activity can be done on railway track, but our focus was on tamping and surfacing, which was two main maintenance activities that have been done by contractor on that road. We had raw data from acceleration response data from sensor that I mentioned, and the idea was to extract the different feature in different domain and see which feature set and which characteristic of acceleration response can be used for predicting the maintenance need of the railroad track. We went with different domain. I mean here time domain, frequency domain, and time frequency domain, and we extract a pool of features from each of this domain, and then we implement some feature selection algorithm and feature classification. And in this case, we use classical machine learning algorithms such as reinforcement learning and also convolutional neural network. And at the end, we was able to detect the maintenance activity a month before a real maintenance activity have been implemented on the road. I mean, there was some sign in acceleration response data before the actual maintenance become obvious for the day-by-day users and for those maintenance teams. So we was using those sign and those features for detecting the maintenance needs of the road. We went for comparing different feature set, and the result was showing that if we go with statistical features such as, for example, maximum of acceleration response data, minimum of acceleration response data, a standard deviation, and some other feature, we can expect a good accuracy in detecting maintenance need of the road. We expand that work, and instead of going and try to see if there is generality between a methodology that we develop for that specific road in US for another project and for another railway system in France. And there was a 3-year project with called Harmotrack, and they was recording a set of data from all railway network of France, high-speed railway network of France. And at the almost the middle of the project, they recorded near to 1.8 million segment of the data from different network, and in each of these segment we have the acceleration response data and corresponding condition of the railway track and geometrical configuration and setting of the track was recording using a specific track geometry measurement systems. And we fuse and we merge data from two different data sets. One data set, as I mentioned, was acceleration response data, and another data set was data that we have from that geometry measurement device, and we combined them together to see if there is any correlation or any other sort of relationship between a specific type of geometrical defect and a specific change in acceleration response data that we can have from sensor that is installed on train. For first work, we went for developing unsupervised anomaly detection model that it was capable to detect and inform us about the state of the track based on input of acceleration response data. It was able to tell us that based on acceleration response data and the feature that was extracted from that acceleration response data, the current segment of the railway track is healthy or there is some problem with that section of track. And that somehow was a starting point for us for working on this data set. And then we expanded that idea for some other railway in same country. I mean, usually when we are developing an ML model, is very good for a specific set of data and for a specific, for example, loading condition, geographical conditions, and environmental condition. But when we want to transfer the knowledge that we have from the first model to a new similar project or similar, for example, railway track, usually the ML model do not show a good result, and we need to go with some other approach. And one of the techniques that usually researchers use in ML disciplines for solving this discrepancy between data set is called transfer learning or domain adaptations, which is the specific sample of or a specific class of transfer learning. And the idea is that if we have a good data set from a different railway line, we can use the first one for training our algorithm and then find those similar features or similar characteristics between these two different lines and try to generalize our model for all different variability that we can have in our input model. So we test and we develop a framework for that case, and then try to implement that for 12 different railway line in France. And results show us that if we goes with not very complicated features such and similar features that we use for our first study, which was a statistical feature of time domain, we can reach the good accuracy in detecting the condition of railway track on another line, not just on the line that we have some data about that, and we can somehow transfer the knowledge that we have from one line to some other line with different techniques in AI and data mining. In another set of project and another work, I had this opportunity to collaborate with different researchers in University College Dublin, specifically for one of the project. I was working with my colleagues, Dr. Robert Corbally, and the idea was to see if we can find a similar set of features and characteristics from a laboratory bridge for detecting damage on that specific laboratory bridge. As you can see, the main bridge was a one-span bridge where a toy car was traveled across that bridge, and it was recording acceleration response data using sensor that was mounted on toy car. A sensor was installed on axle and also a bogie of that car. And when it was traveling across that bridge, it was recording acceleration response data, which was from interaction of the tire and the surface of the bridge. And we use that data somehow for detecting different condition of the bridge, such as a CZ bearing and cracking, to see if we are able to detect different condition of the bridge based on acceleration response data. We develop a methodology for doing that. We have the acceleration response data, and then we use feature engineering for extracting the data from that raw acceleration response data that we can have from the bridge. And then for selecting the most suitable feature that can be used for detecting crack or CZ bearing on bridge, we went for different feature selection algorithm. That is, we have different techniques for feature selections. I don't want to go into detail for that, but in this case, we test more than 35 different combination of ML model and feature selection model to find the best one that can be used for our case and for damage detection on that laboratory bridge. And the final output and final things that we was figured out was that if we select a good amount of the feature and engineered feature that have the some knowledge of that structures, no matter what ML model we are using. I mean, specifically in case of shallow models such as neural network or support vector machine or k-nearest neighborhood, if we have a good feature and if we have good input, no matter what model we are using, in most of the case, accuracy that we can detect and accuracy that we can have is acceptable, is more than 95%, and it can be acceptable in engineering principle. We also did some sensitivity analysis on different sensor locations and to see which one can be the best feature set for our case and sensor that was closer to the bridge, specifically those sensors that was installed on axle have more sensitivity to damage on bridge. In similar case studies, but for different application, we went for detecting different case of defective wheel in collaboration with University of Porto, and they have a specific model, a finite element model for simulating terrain track interactions. And one of the main fault or defect that terrain system have is wheel flat and polygonal crack that we can have on wheel. So the idea was to see if we can go and use acceleration response data that we can record it using a series of sensor on track for detecting the condition of the wheel. You can see those sensors that is shown there as yellow, and then we use that as input of our model. We test and develop a framework for feature extraction from raw acceleration response data and developing unsupervised model for detecting the condition of the wheel flat. And results show us that we can go and detect a different class of the wheel flat with acceptable accuracy, and we also extend that for different type of train, I mean passenger train with different sensor setup. And the idea was to see if we can have a good understanding about the condition of wheel based on sensor that can be installed on track or on sleepers or between these two. And results show us by proper feature engineering and selecting the best features, we can select each of those sensors. The location of sensor is not very critical, and the most important part is to have a good set of characteristics from the raw acceleration response data that can be used as input of our ML model. That was some a very compressed summary of some of the work that I've done on transport infrastructures. But as I mentioned in the beginning, my goal was to see if we can go with different discipline of civil engineering and different discipline of engineering, for example, in field of infrastructures. And we test some of our idea in wind energy infrastructure. During the time that I was working in UCD, I had this opportunity to collaborate with a very talented group of PhD students. And with each of them, we tried to look at the problem from a different perspective. I will show some of the work that we have done and the project that was mostly led by the PI and the leader of our research team, Dr. Malik Jafarian. In first work, the idea and the goal was to detect and scour the depths around monopile of offshore wind turbine using sensor that can be installed on tower of that wind turbine. We went with similar accelerometers to be installed on tower, and then we use those acceleration response data as input of our models. Somehow, all of my research work is focused on using acceleration response data and, in some cases, strain gauge data for detecting the condition of the structures. When we have that acceleration response data from tower of the blade, the tower of the wind turbine, then we can develop a methodology for that to be used in progress for detecting the scatter depth. And we figure it out if we goes and select statistical features such as I mentioned, a time domain, a statistical feature. We can have a good accuracy in detecting different scatter depth, and specifically we can choose a set of sensors that can give us a better responsibility and better detectability for a scatter depth. And in our case, the sensor that was closer to the sea level has higher sensitivity to scatter depth. We also, in another research project, I was working with a PhD student in our group, Mahdis, that she was working on idea of how we can detect the crack and length and type of crack on a specific type of wind turbine with placing sensors on each blade. I mean, specifically in this case, sensor was installed on 12 sensor was installed on one of the blade of a wind turbine, and it was recording acceleration response data in different conditions with different wind speed, and we was using that data as input of our detection model. One of the specific challenge for that project was that acceleration response data is very prone to environmental condition and is most of the time is affected by environmental condition, and sometimes the change that you can have in acceleration response data is very dominated by environmental condition of, for example, heating and freezing. So we developed a methodology for removing those influence and selecting the features that have less sensitivity to temporal conditions, and also have higher sensitivity to the crack length and depth. And more detail about that methodology can be seen in the original paper. I was also collaborated with another PhD student in our group, Theo, where we tried to develop a methodology for detecting different event for a specific SHM challenge. And there was that data set was covered 3 type of fault somehow, and the idea was to, can we detect, for example, pitch drive failure a day or 2 days before real failure based on acceleration response data and based on the sensor that was installed on different part of the wind turbine. And you can see some of the sensor that was installed on main shaft, and we developed systems where it was interpret and extract some input from some feature from raw acceleration response data and using them as input of a clustering model. And in all of those 3 cases, I mean, for detecting pitch drive failure or aerodynamic imbalance and icing event, it show a good and acceptable accuracy in detecting the event. The final project that I want to show from the time that I was working in UCD is a project that started almost 2 years ago with another PhD student in our group, Mahmoud, and the goal was to see if we can transfer a knowledge and the information that we have from one wind turbine to another turbine in same farm, or in some case to another farm. As I mentioned in the beginning, most of ML model are very good when you are working with them for a specific example, or for example, for a specific wind turbine or a specific train or a specific bridge. But when you want to map the information that you learn from one bridge or one turbine to another turbine, it in most of the case we are facing with lots of inconsistency and low accuracy, and that is the one of the main challenges in a structural health monitoring discipline. And different researcher goes with different idea for solving that, and one of the well-known approach is population-based structural health monitoring, where we are trying to find a common space between different structures and try to train or algorithm based on that common space instead of going for individual structures and so on. So this series of work, we went with idea of transfer learning between different wind turbine, and we test and develop a different algorithm. And at the end, we figured out if it goes with frequency domain features, we can have acceptable accuracy in detecting scour depth in different wind turbine in same form, and also we can map data to some other wind turbine in some other form by using knowledge transfer and domain adaptation techniques. Another piece of work and another branch of work that I was working and currently is my main research work is how we can use AI and data mining techniques for solving some of the challenge that we have in transportation, and specifically for how we can use data mining techniques for ITS and ITS infrastructures. That field of work from my side is started from almost 3 years ago, when I went to Czech Republic for a month, and I was working in CDB in Brno for a specific project. And the idea was that in that time they were trying to check and study the use case of some specific sensor that have been developed by their team for detecting number of vehicle and also the type of vehicle and flow of vehicle somehow based on IoT device which was very small and with high and good battery life, which can be installed on road. But the challenge for that specific type of sensor, which is the background and the methodology of the work is similar to loop detector, which is work on based on magnetic field, but is more condensed on a specific type of sensor. By the way, the main challenge was that how we can improve the detectability and classification performance of that type of sensors for knowing the number of vehicle and also the condition of the vehicles. Based on the previous experience that I had for working with raw data and fusing and merging different data, I was trying to explore different characteristic that we can have from raw magnetic data from that specific sensor, and trying to find a correlation between those features that we can extract from magnetic raw data with different vehicle class, for example, with bus or car or HGV and van, and try to find a better match between different class and different characteristics of the magnetic raw data. And we also compare our algorithm with data and with the class that we have from the camera, and result was quite good. It showed up to 8% increase in classification performance compared to what they have done before, and it was a starting of some other project with CDB. Also, in another project that I was working with my colleague Amir Reza in UCD, we was trying to find a way for predicting travel time using data from AID and TMU, or those loop detector on M50. And the idea was to find a best set of features that can be used for predicting travel time from a pool of features that we can have. We can go with the number of vehicles that we have on a specific section of the road, or with the day or the time of the day that we want to predict for use as input for predicting the travel time of vehicle on that portion of the time. Or we can go with different weather conditions, we can go with different type of vehicle, and with a speed that is set and have been shown to driver. And at the end, we figure it out if we a methodology and a framework developed for feature selection, and we figure it out the most important feature for predicting the travel time is number of vehicle that we have on that segment, and that can be used and appropriate way for predicting the travel time for each segment of M50. That was my starting point of my work related to M50, which is the busiest motorway in Ireland, but was not the last project. As I mentioned, from 2022, I moved to Ronald O'Donovan, which work on different aspects of civil engineering discipline, but I mainly work on a specific project called EMOS, which is abbreviation of Enhancing Motorway Operational Service, with the goal of improving the driver experience from when they are driving on M50 by showing a good speed and cautionary speed to them, and also giving them more information about the condition of the road, about the number of incidents that happen, and so on. One of the challenge for this work is that we have data from different sources. I mean, we have data from those, for example, emergency services that goes and responds to any incident on roads. We have some information from sensor that have been installed on road that for detecting number of vehicle and road, some ANPR camera and CCTV camera, and also some weather stations that is used for knowing the condition of the road and the weather condition on each section of the road. We also have some information from operators in control center that assign a speed for different section of the road, or those advisory speed for driver. So one of the challenge and issue was, first of all, somehow data fusion of all of this data source, and our team or data team in ROD have been developed different software and tools for merging different data from different data source to have, for example, a dedicated software and dedicated dashboard to be able to see the current condition of the road, and also be able to extract some insight about the reason behind some of the incident, reason behind some of the congestion that happen on the road, or reason behind some of the other problem that we can face on road. I don't want to go into detail on different software and platform that have been developed by our team in ROD for this specific project, but I just want to show two of the recent projects that I mainly work on that in previous months. One of them was to see if we can find any correlation between the different weather conditions and the possibility or probability of the incident on road, and if there is any impact or direct impact on probability of incident, how we can reduce that probability. The second or the plot that you can see in left is from one of the tools that have been developed by our team for showing the traffic condition and queue propagation in each direction of M50 to show us better understanding of how it start, how it propagate, and what was the geographical extent of the incident and what was the time extent of each incident. Specifically for this case, we test different weather conditions and the different weather features such as rain, precipitation, surface water thickness, wind speed, grip, and road temperature. And at the end, we figure it out that the best feature that we can somehow use for knowing the condition of the road and also informing the driver is grip and surface water, because precipitation have very non-linear behavior, and we cannot rely on that, for example, for long term. But surface water and grip is more incremental features and also have lots of effect on the capability of the driver for having a safe trip on the road. So we are currently monitoring that, and we also currently working on another project which is mainly related to AID fault detections. As I mentioned, on M50 we have lots of sensors such as CCTV camera, ANPR camera, and also lots of different type of loop detector that is used for knowing the number of vehicle and average speed of them, and also some other statistics. But one of the challenge from asset perspective is that those sensor can sometimes show faulty data, and we develop an approach first of all for detecting those faulty output of the AID sensor, and also for predicting the upcoming fault in different batch. For example, in next 7 days, what is our expectation about number of AID that will have some fault and how we can approach to them. That was some of the work that I'm currently doing already related to ITS. As can be expected, I also work in some project related to structural health monitoring. I don't want to go into detail because in first part of presentation, I gave a good part of my presentation to structural health monitoring, but just to acknowledge the work that has been done by our team for a specific project that have been developed for, we developed a platform for health monitoring of Humber Bridge in UK, where a dedicated software developed for showing the current condition of the bridge based on sensors that have been installed on bridge, and also being able to monitor the condition of the bridge when a specific live test is running on the bridge. Specifically for one of the challenge for this project was the number of and the frequency of the data that we have, and our team developed a dedicated pipeline for reducing and size of data and be able to plot data in different way and be able to see correlation of data with any temporal condition and so on. At the end, if I want to summarize what I mentioned in the previous slide, is that I start my research project and my work in ROD with some questions on how we can correlate civil engineering and find a connection between civil engineering and data mining. And I try to develop a different methodology for different field of civil engineering, transportation, wind turbine, and also ITS. And one thing that I figured out is that when we have data, the most important part is to select a suitable set of features that can be used for different ML model and data mining techniques. And if we have a good understanding about the physics of problem, we can expect to have a good output from our ML model. At the end, I want to acknowledge all company and organization that fund some of the research projects that I showed to you, or some of the project that I have the opportunity to collaborate with different organizations. I also want to thanks all of the researchers in different universities that I have this chance to collaborate with them in different research projects, and also my colleagues in ROD that I'm currently working with them on different projects related to ITS. That was all from my side, and thanks for your listening. If there's any question, I'm happy to answer.
Yeah, thanks, Ramin. I mean, it's quite impressive to see your extensive experience across in the railway, wind energy, and also the intelligent transport. You're currently working with the Audi, I would say. Quite impressive. Yeah. So for any question, yeah, you can free to ask, or you can just type your question in the chatting room. Yeah, just free to ask. And also, actually, we got one question. Okay, we got two questions from. Yeah, if you can see the chatting room, actually, Ramin, there's
Yeah,
one question
let
from
me
Matt. Yeah.
let me find that. I can
Asking.
find it. Yeah, let me. Yeah. I don't thank you. Yes, we have more than 55 paper on different field of structural health monitoring and other related topic, and some of the results that are shown to you came from those research work that I have done. And if you search my name or some other colleagues such as Dr. Manager, you can find some of those papers, and you can also send me an email. I can share you some of the project that we have done. But yeah, we have quite a lot of paper on those work.
Yeah, and one more from Matt. Can see it. That is more about the talking about efficiency and also the trust force.
Yeah, let me check it. What is the definition? If I correctly understand your question, Matt, the part of the project that I've shown to you was mainly a research study that I have done during my time in UCD. And for those work, we was comparing the performance of ML and machine learning compared to day-by-day use of some other techniques for maintenance of the, for example, railway track. But in case of my current job in ROD, where we are using, for example, AI for detecting the fault of AID or loop detector on M50, it's show a very promising performance. I mean, instead of sending our maintenance teams to check each of the AID independently, we are somehow have estimation of number of AID that we may face some fault in upcoming weeks. And by knowledge that we have from the history of the maintenance that have been implemented on those sensor, we are able to predict the future conditions. The main thing is that in most of the case we have a bunch of data from different sensors. So and accessing the data is not challenging this day, and also somehow with different ML models and specifically large language models such as Claude or ChatGPT and those things in this day, also having a model is not very challenging. The most critical part is to having the engineering perspective to how we can correlate these two piece of things together for first of all gain some efficiency and also reduce the, for example, labor time for going and checking the infrastructures or AID, and also have better responsibility and better response about the future condition of each of the structures.
Thanks, Rami. So I hope it responds good for Matt's question. We got one more question actually. Yeah, we got response from Matt as well. Yeah, thanks, Matt, for the question. I've got one more question from talking about the application using AI for construction and oil and gas projects. Can you see that, Rami?
Yeah, I can see that. It's for the question that Salim was mentioned. Definitely, AI and data engineering can be used for different phase of the project, not just for performance monitoring and health monitoring of that. It can be also used in design phase when you want to design a new systems, for example, for oil and gas project or for optimizing your structures. There are a different approach that you can use the AI and data mining, specifically for optimizing your design. You can test not just one design style. You can test 100 different combination of, for example, material and design systems, and use AI for make some predictions and some automations for doing those design instead of doing design one by one. We can go with optimal selection of the material, optimal selection of the for example, different size of the material and those things, and all of them can be done in a loop of ML model for, as you mentioned, reducing the risk of wrong design and also reducing the risk of having a problem in design life of the structures.
Thanks, Rami. Actually, I got one question. Actually, I type here as well. Yeah. So, as I know, you moved to industry, right? So, from the, let's say, from the person perspective from the industry, so what's the main difference you can see? Regarding the demands and the expectation, as a company, rather than the researchers in the university, I would say.
Yeah, the thing is that lots of company like right now are trying to, specifically with this new software and hardware and boom that we have in AI industry, and the term of AI becomes something that all known about that. Most of company are trying to find a way that they can use AI in their day-to-day work, and some of them are looking for more advanced use of the AI. For example, specifically, for example, in our company, we are trying to use it for our task and for project that we are delivering to our client. For example, for health monitoring or for predicting the condition of the ITS infrastructures. But it can be also used for day-to-day work, such as, compressing some email, extracting some insight from Word file. And one of the things that researchers that in civil engineering and AI can be targeting is that this day more company are looking for a person and with the guys that have knowledge of both part, not, for example, knowledge of, for example, just civil engineering or knowledge of artificial intelligence. If someone have the capability of a formal civil engineer with some knowledge about artificial intelligence and data mining, it can go with combining different idea together and proposing new project and going with different tasks. And we will see more project on using data specifically in civil engineering in future, similar to what the project that we have currently in most of the countries.
Thanks, Rami. We got last question. It's talking about training and time efficiency, I think.
It's depend on the project and it's depend on the size of model that you want to go. I mean, for some of the research project, we had the data, for example, from 4 years of collecting data, and then we was using 2 years for training and 2 years for testing. But based on the size of data, training time and testing time was different, but is completely depend on use case, and also is depend on what we want from our model. I mean, if we want to go and if we have access to a big data set, then we have the opportunity to select part of it for our training. But if we have a small size of data set, then we don't have in some other choice, and we need to stick to that data and work with that set of data that we have.
Thanks, Ramin. Thanks for all the question, and also I will thanks all for joining today's Lunchtime lectures. Yeah, very appreciate. Thanks, Ramin, again. I will see you
Thank you
in
so much.
Dublin,
Thank
okay?
you. Thank
Yeah.
you.
Thanks,
Thank you.
Ramin.